Actually,
Sorry.
I'm saying like before those doubts actually there were doubt in assignments also, like this
Oh,
week, sixth week,
okay.
seventh question.
Okay. What's the question?
Like, like the question is there. There we went. We want to find like we need to find two equivalent shapes, such kind of thing.
Okay.
The matrix we get same equivalent matrix, right? Like that kind of.
Okay, maybe I just open it. Week 7.
Sixth, sixth week.
Just week assignment.
Seventh question. You know,
Yeah.
yeah, this one.
Which of the following options represent an element with same elemental stiffness matrix as shown in the figure? No numbering is done in the respective figures. Okay. This one is like if the element is same, then and the numbering is also same, then the stiffness matrix will be same irrespective of the orientation. Here at least first thing we can check is between node 1 and 2 the length is a. We can check that. First
Your
option is
voice
direct.
is not clear.
It's not clear.
Yeah, sound is okay, but there's it is like
Nice.
not that clear.
Yeah. Hello.
Yeah,
Is it better?
yeah, it is better.
Okay. What I was saying is if the element is same and the numbering order is same, then the stiffness matrix will be same irrespective of the orientation of the element. So, like between nodes 1 and 2, the length of the line is A, and that we can check. First option we can directly eliminate because between 1 and 2 it's not A, and second option 1 and 2 A, and third option also 1 and 2 it's A. Fine. Second one is between 1 and 3 it is B. Oh, it's 1 and 3 it's not B, and 1 and 3 it's not B. Okay. Yeah. 1, 2, 3, 1, 2, 3. Same elemental stiffness matrix. It's not matching exactly, nothing isn't matching exactly. Okay. 1, 2, 3. Hmm.
So none of these.
Yeah, it doesn't look like any of this. Yeah. Is
So
that the
basically,
answer?
the thing is like orientation does. Yeah. So the thing is like orientation doesn't matter.
Orientation doesn't matter, but here it should be like numbering. We need to check it because we want to have the same stiffness matrix. Like one is starting at this one, but wait. Yeah, I think we can write the options after that. Did you get the solutions for this?
No, I need to submit this. Today is the last day.
No. Okay. Yeah, none of them are. See, it's like if we the ordering of the nodes matter, and here one is coming at this bot like right angle. Similarly, it should be same. Otherwise, like it's just it will be scheduled like matrix elements will be.
Yeah, so only like orientation is same and it's even if the distance is same, let's say in the option B, if
Yeah.
1 to 3 is the distance from 1 to 3 is B, then will it become the right option?
Sorry, 1 to 3 is B and 1 to 2 is A.
Yeah, yeah, in
Yeah,
option B.
like in
Then
option
will
B,
it
let's
become the
say
right
if it's
option?
like two is this is one like node number one, like at the hypotenuse, sorry, at the right angle, and other are 2 and 3, then it's will match. Otherwise, no.
No, the one thing is like you told that orientation can be anything. Second thing is the distance between the two nodes should be the same. So
Yeah,
I
it's like
am saying that if we make this, so I am
uh,
saying if we make this distance 1, 2, 3 in option B is B, then will it become the right option?
yeah. If in the B, if it's like 1 2 is 1 2 3 B, yeah, yeah. Eh, and right angle should also be maintained.
If right angle is maintained, then the only condition is like then it should be as same as the
Yeah,
whatever
basically the
given in the
element shape
question,
should
right?
be exactly same. Just the it can be rotated anyway. Element shape should be exactly same, and also numbering also should be the same. Like where it
Okay,
starts.
so
Just if this one,
so
if
we
you
can
can rotate
easily
anyway, it's fine.
okay. And why does rotation doesn't matter?
We are rotation. Mhm. Okay, in Jacobian would be same, but still rotation. If you will just see, did you try to find out and see how it would look like for the stiffness matrix? This is 1 2 3. If we want to write, generally it would be something like n transpose and dx dy, um, something in this manner, right? In like for standard, maybe like thermal conduction problems. Okay. Mhm. It's first of all, it's an integral problem over the area, like the stiffness matrix, whatever you are getting, it's an integral over the area, right? So it's like
Yeah,
irrespective of the orientation of it, it shouldn't matter this integral. But you understood? Like it's like an whole thing is integrated over the area.
yeah. But in assembly, it matters.
Yeah, well, you have this like shape functions. N would be like depend on N1, N2, N3 will be different, right? And depending on this node numbers where you are taking, so this will differ. So accordingly, stiffness matrix also will change.
Yeah.
Like that's why. So even the shape should be same and also the numbering should be same.
Okay. And while assembling, rotation should also be same.
This is only one element, so there's no assembly in it. If there are multiple elements, then yeah, even assembly should be same. This is only one element, right, in this case.
Yeah.
Yeah,
Okay, sure. We can go for that those questions.
yeah. So one more question last time you asked was about weighted residual error.
Yes.
Can you once again tell me the video which he told that? We can, if you remember. It was in which, right? Do you remember the lecture name and like?
Yeah,
Mm.
actually, the thing is like doubt is like this. Like it, you said one thing that weighted
Yeah.
integrals of error are exact integrals. There is
Yes.
no assumption in it. But the only assumption is that we are assuming some function. So my doubt is like how weighted error
Yeah.
is and given exact.
I think maybe the examples where he was saying the integral. It's like this one. If this is the weight function, so if you take any specific, if any specific w is chosen, then the error won't be zero everywhere. The average error is zero. Average error is only zero.
So means weighted. The first thing is like error is introduced when we assume that function. Obviously, we don't have that function, so we assume something. That's why an error comes. We
Uh,
multiplied that error with some weight,
yes,
and it is
yes,
said that in an integral sense,
yeah.
in an
This is
integral
like
sense,
error function.
we are
Like
making that error zero.
yes.
Yeah, sure.
So if we
Now,
take
oh, like because error, yeah, please go ahead.
yeah, if we assume any specific function for w, then for that specific function it won't be zero, but the uh, average weighted error will be zero. But if w is arbitrary, like any function, like you can say arbitrary means for all, it works for all function functions like that. I is equal to zero, then the error is zero everywhere. Yes. Great.
What does that mean actually? Error is zero everywhere.
Yeah, if W is like if you don't take any specific function for W, if this I is equal to 0, like if W of f of x dx is equal to 0 for any value of W, for all values of W, then f of x is equal to 0. But if you choose some,
Yeah,
let's
that is what
say,
the doubt is.
yeah, no, I think sir
This
was
is the
saying a
doubt
bit,
actually. How?
yeah, I think,
But let me complete the thing, guys.
yeah, yeah,
Yeah, the doubt is like goes like this, that because he said that because the error can't be zero, because we are assuming some function and we don't know that function, so there is an error. Because we do not make error zero at every single point, so we make it zero in an integral sense. Weighted error, we make weighted error zero in an integral sense. That is what he said. So that like means if some at some point there is positive error, at some point there is negative error, total must be zero. That is what he said. So the doubt is, you said that when we calculate weighted errors and make it integral equals to zero, there is no assumption in it. Like my question
yeah,
is why we are taking this weighted error, how it becomes how we come to this conclusion that if we multiply with some weight and it comes out to be zero.
yeah, you should focus on this one actually.
And
This is important. Like, let me say one example. Like, generally, there is one method called where, like, depending on weight functions which you assume, some they are called different with different names. If you take the W weight function is equal to 1, and then it will be your error. And if you make it to 0, then this is one of the situation. And you can take W is same as I think f of x
it's
probably.
square or something.
Yeah, it's square maybe. Then you will get integral as x square dx, x square f of x dx. So in these specific cases, just weighted average error is 0. But at each point, f of x won't be 0 in these two cases. Like because you took for some
Yeah,
specific W and then you are proceeding forward. So this is what it happens. But let's say instead of taking like this, let's say you are taking a function like this, W as Ni of x times Wi. Okay, but here approximation comes. So even here it won't be 0 exactly. But if we, let's say if there is any way if where you cannot doing any approximation, if you are able to find the function, then this would be 0. But once you do
yeah,
approximation,
like
it,
how we come up to,
yeah,
yeah, how we come up to this conclusion that if I multiply it with this function w with this function and integrate it and make it zero, like how this expression comes that we I just multiply error with some weight function and make its integral zero.
it's like nothing like it's like so. Are you saying like why are we taking especially this expression?
Yeah,
Because we want to make the equation into integral format actually, which is more easier to solve than solving the differential equations. And this is one of the method to do it.
Uh, uh, I I came up with something. Please check me if I'm wrong.
Yeah,
The thing is like I approximate some function. So if just draw some random function.
yeah, like okay,
Hmm.
okay,
Yeah, and now our assumption, our this is actual function, and we are
okay,
assuming. And please mark it some above and something below, like some function near to very close to it, but some portion of it is above
yeah,
this curve and some is below.
okay,
Yeah,
something
yeah,
like
yeah, such kind of thing. So
okay,
this is our assumption, and
okay, let's
now
say okay,
when I get now I when I calculate the error, it is the difference between these two functions,
uh, yes,
because if I put because I take the right hand side to the left hand side and make it zero, so means kind of thing like the error is difference between those this
yes,
function, right?
yes,
And this is one element.
uh, this is for one element, okay,
This
yes,
is one element.
okay,
Okay. Now please make one another curve of error where some portion is positive and some portion is negative.
function or error, okay, something like this,
Yeah, yeah, yeah. Same,
okay,
same, same. Yeah, such.
yeah,
Now, please mark like it is 1 to 2 node. It is kind of on x-axis. It is 1 to 2.
okay,
Same is here. Same in the first curve. Same
okay,
in the first curve also. 1 to 2. Yeah.
okay,
The second one is of error between
okay,
those two curves. So
okay,
here,
yeah,
yeah. So now my question is like I integrate this error and make it zero. But that is fine with me. Like I am taking weight function as one.
yeah,
But why I need some different weight functions to like I have
uh,
multiplied with x square and then like
it's
why
like
can't we generally like directly integrate this error and make it zero? Because then also we get positive error and negative
yeah,
error
like
summation zero.
yeah, if you take like when w is equals to 1, that that's what you are doing. Like integral of error dx will be 0, right? In these
Yeah,
cases, could be sometimes it would be like drawn like this. Even if it's like half positive and half negative, then the average would be 0, but it won't be exact function, right? But
yeah. So why we need this w? Like how we come up with this conclusion that we need different kind of the w and those could be shape function. Then it comes, then we can take it as same as shape function in
yeah, actually, like
irreducible
with
method.
different, while taking different types of W, you can play how it would be. Let's say if you take something like W is like maybe sign of error, okay, like whatever the error sign will be same like, then probably you are making it everything to be positive, something like that, or else depending like by
What
changing you can,
what
yeah,
I think, like
yeah,
what I think we have done this randomly just because the
yes,
forward after some time the maths become complicated. Like if we have weight function, then we can easily calculate it because we can shift the differentiability to the weight function. That is the only use of weight, what I
W.
think.
Like
Yeah,
while
the
choosing
only
W1 X square randomly. Are
no
you
my thing is like
telling about this one and X
there is
square?
no point of no, I am saying there is no point of using weighted errors. We can use integral error equals to zero. The only thing we use weighted error because we can shift the differentiability and it helps in further calculations.
Uh, no,
Because there is
that's
no
not the.
such
That is one
like
of the advantage, but that's not the only reason why we do it. Because another thing which this is actually one of the important thing where like we start although we start with this, but we go to generalized W where error is supposed to be zero everywhere or at least at the nodes. Yeah. So we start at this, but we make it more generalized, and we when we take W is equals to NIWI, it implies that we are taking some arbitrary general function, some general function, instead of taking some specific function. Get it? And if you take when we are taking some general function and that integral works for any general function, then its more solution is more accurate than in any specific case. And
but
obviously that
like why?
shifting the different derivative is also one of the advantage of that.
No, but how we get more like if this curve is made of error. If I multiplied this error by some weight function, how
Yes.
is this going to help me to get a better solution?
Um, See, this one error you are multiplying with a weight, and let's say if you are multiplying with just one, this will be your area. And let's say you are
Yeah,
multiplying with h, then this would be your maybe second one, something
yeah.
like that. And maybe one plus h could be something else. It could be different errors, different values. And when we are taking general, it works for any kind. If you multiply with anything, still will be zero. It's like bit of error is will be zero everywhere. Even there's some assumption here. It's like we are not taking any general function here NIHI. It depends on NI order, but still, I will tell you one thing. Let's say um, your function normal. Let's say error function is on of order. Let's say order maybe third order. Okay, and double n uh, of its also order 3. In this kind of case, something like in the in that space, something like error is of order polynomial of order 3, and you are multiplying with an arbitrary polynomial of order 3, and you are saying it's will be 0. Then it's like weight would be something like I'm saying a plus bx plus c x square plus dx cube, and some error function you are getting, and you are saying this integral is 0 everywhere. Fine.
Yeah.
So just by changing this integral can change a lot, and but still you are making it to 0. It it shows that like f of x will also be 0. There will be Hmm. First thing, maybe like one thing, like before going for any kind of approximation, don't think in terms of approximation. Just let's just say you have some error function. Okay, this is your error function. It is zero. Some error function. Okay, no approximation. What it means is it is zero everywhere. Okay,
Error is zero everywhere.
yeah, error is zero everywhere. Okay, I'll just write maybe error of, okay, some error function, error of x, it's zero everywhere. Okay, but let's say if you have taken this one, integral of x dx is equal to zero. It means some L1 and L2. Average average error over the length is zero and may not be zero everywhere. Okay, this is fine.
Yeah.
And let's say L1 to L2 and h times error of h dx is also zero everywhere. Same it will be. Okay, it will be some weighted average error will be zero. It's
Yeah.
not average error, but weighted average error will be zero,
Weighted
and
error.
error may not be zero everywhere. Okay, let's say what if I say this one first expression is zero and second expression is also zero, and then let's say maybe 1 plus x error of x is also zero. Okay, and all these three expressions satisfies.
Yeah.
Okay, in this case you can come up with some functions which are just positive and negative matches, and then it's done. In this case,
Yeah.
in this case, probably still you can find out a different way. Okay, maybe something like error is 1 by x of this, something like that. Still you can find. Let's say this and this both cases it should valid, and also it should valid for this. So in the only possible cases would be like error should be zero everywhere kind of thing. Like as you are saying, like it works for any kind of weight, then error will be zero, and so on. If you say the only like number of possible cases of error would be reduced to only arbitrary solution where error is zero. That is that, like if weight is any function and this integral satisfies for any function of weight. Any weight. Okay. So till now there's no approximation. Don't think about in terms of approximation. Just you have a function which is error function and you have some weight function. You are integrating. Is this clear?
Yeah. And
Yeah, right. And
yeah, because by multiplying through any function,
yeah,
the integral value still remains like
yes,
zero.
yes, still zero, right? This is the actual main uh, concept for it, but for specific cases, they are called don't come into approximation till yet, like approximation of the error or approximation of anything. So even before even approximating it, this is the uh, like integer concept. Okay, so uh, and let's say right now we have some error function and some weight function, and for different, let's say just if w is equals to 1, this is you'll get some solution, but that solution error won't be zero everywhere, but it is one of the method, and w is equals to x.
Yeah, so
It's
the
not
only,
accurate.
yeah,
Yeah,
yeah, excuse me. The
yeah.
only use comes so the end conclusion, the only use comes out to be the same thing, because we are multiplying just because to shift differentiability and doing the computation, it becomes
No,
easy
but
to multiply
uh,
through some
we actually don't.
appropriate way.
No, no, we don't stay with here. In FEM, actually, we use we go one step ahead of this, and I am coming to this. Here, in there's still in these cases, solutions are still not very uh, not accurate. But in these cases, what happens is one thing which you do is you increase discretize the elements a lot. In a sense, it's like instead of saying in the whole domain, let's say this is your error, let's say between L1 and L2, and if you say one element, this would be zero. Error is zero, like average error is zero for this function. Okay, but let's say I took discretize it and take it two elements. In that case, it would be like in this also it should be zero, and this also it should make it to zero. So it would be better solution than this, right? And let's say you have increased it more number of elements. Fine. Even each element it should be make it to zero, right? So on discretizing the decreasing the size of the element, you can approach to better solution even with this weighted functions. This is one thing, like with fixed weight functions. By reducing the element size, more accurate solution can be obtained. Okay, okay. So then we are coming. Let's say this is even this one. Okay, we are here. I will tell one more thing. Then we are coming to w of f of x dx is zero. We are saying w is ni xi. I'm not sure if did sir say a case where we are taking w as ni, right?
Yeah,
Same as shape functions. So when you take w as ni, uh, it's indirectly you are taking actually w as ni wi, but I showed you in the previous tutorials like wi gets cancelled out. Okay, so this would be like depending on the order of ni, w would be like arbitrary polynomial function, like if polynomial of order same as n, let's say n is of order alpha, then W will be arbitrary polynomial of order alpha. So at least within that polynomial range, W is any arbitrary polynomial. And even we approximate this function with same something like ni ui or something. So even function we are approximating within that using this polynomial. Okay. So same here you have this error. Let's say we are approximating it with linear, this one, and weight is also linear. And you, let's say you took only one, will take four elements. Okay. So this will be
No,
your
this is the
approx.
curve. This is
This is your f of x, like error. Let's say.
error, not a function.
Ah, error itself. This is error itself. Error itself. It's basically uh, you have, let's say, this is your equation, something like that. Then you would say dou dot sigma minus b is equals to 0. So this will be your function as well as error. Both error and function would be same because let's. This is your function. What is error? Error will be like you are supposed to get 0, right? Originally,
Yeah.
it's fine,
Hmm.
fine, right?
Hmm.
So when you want a function is equals to 0, then error is uh, basically the function itself, whatever the function value will be. Okay. So I'm say what I want to say is like when you approximate this function using linear thing, this function will be linear, but also you are saying this weight also will be some arbitrary polynomial, and then for that arbitrary polynomial, this whole integral will be 0. So it's like you're not fixing W to like 1 or X, which is like lesser accurate. This one, it's like it's working for more number of functions, then it would be like more accurate solution.
Actually, this is difficult to get actually because like even if we take this graph as function and like first element if I take
Yeah.
then this is error. Yeah, this is error. So I need to make this error zero.
Yes.
Like in the first element, I need to multiply this error with some weight function.
Yeah.
You are taking this weight function as linear.
Yeah.
Now we multiply both these things and we need to make zero.
Yes. So this is
So
this is
after
your
multi
actual f of x. This is your approximated f of x. Okay. So this one you are multiplying with any w, like w I said is any linear functions. So you multiply with anything, still it should be 0, means this f dash x should be 0. Right. In this integral of w f dash x, you are approximating f of x by f dash x, means you are removing like substituting f dash x instead of f of x. In
yeah
this right, and you are saying w will be like,
yeah.
and okay, this one it will be 0 everywhere.
Why? No, 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 no. We have assumed f dash x is f dash x is approximate function. Fx is original function.
Yeah,
If I
yeah.
multiply what I have to do to find the error is fx minus f dash x. That would be the error in such case. What we are doing by taking the left hand side to that side is the same
This is not
fx
what
minus
we
f dash
do.
x.
This is not what we do because we don't know what is f of x is. Okay.
Yeah, but
Then
kind of
how
same
can you
thing.
find the
Kind of
error
same thing.
f of x minus f dash x? This you cannot find out. Right. But we know that f of x we want
Yeah,
to be
but
0. So we find error is f, this one. Error is f bar of x.
f dash is
Hmm?
okay. Leave that out. Just leave it because it is confusing. Because just above in the previous slide, just move
Yeah,
a little forward upward.
yeah.
Yeah, here in this sigma, just that
Oh,
del
this one.
dot
Yeah,
sigma. Yeah,
yeah, yeah,
there. Yeah. So when you take this del sigma minus b,
yeah,
right? But
yeah.
there, yeah, in this equation there are some x coordinate, y coordinates,
Yes,
right?
yes.
Be- or I can say some u will be
Yeah,
there.
yeah.
Okay, unknown
Okay,
variable,
okay.
and because we are putting some different values of that unknown variable we don't know, and we are putting something. That's why it becomes an error. If I know exactly what those u are, then I get the exact solution,
Yes,
right?
yes,
Because we have put some different use, it become a approximate solution. So now
yes.
now this equation is, yeah. So now if I'm so from the curve we can say that, if let's say if I am putting original use in this,
Yeah,
then
yeah.
fx is equals to this, fx is equals to this equation, and it is going to be equal to 0. But
Yes,
when I put some
yes.
approximate use that are in f dash
Yeah,
x,
yeah.
then this is not equals to 0, because we have assumed the
Yes,
solution.
yes,
Then it is not equals to 0. Okay.
yes.
So when it is not equals to 0, so uh, then acha, that will be the error. Okay, yeah.
Yeah, there will. Yeah. So when you take this linear, there would be error. It's fine, but at least with this approximate solution, itself we try to find out the solution. At least f dash x is equals to 0. Like when we put in f dash x, we are trying to solve for f dash x. Solving for f dash x, not it is we are solving for f dashes such that this one wf dash x dx will be 0.
Yeah, it's okay. Yeah, it's nothing. Yeah. Okay, I think it's take. Okay, we can come to the second order. Otherwise, it would take all the time.
Okay,
It's okay.
okay. Actually, the problem is like we do approximations at many places, and every place there would be like error creeps into picture. Uh, so it's difficult to differentiate what like which kind of error are we talking about and which approximation you are talking about. It's fine. Okay.
Oh,
Next, you,
yeah. So, like bilinearity, the second question is like bilinearity, how it help in FEM formulation, and how it make a solution consistent. And the second thing is the relation between bilinear function and symmetric K matrix, because for both we need same conditions.
bilinearity. What I found out is that when you say bilinearity, it's like you will have some consistent solution. That's the only thing which I found. You will have some. You can say that if your equations are bilinear, then you will have some solution. And then for Symmetric actually, if the matrix is not just symmetric, if it is symmetric positive definite, then it is invertible. So these are uh, properties they show because they want to talk about that whenever they say bilinearity. By saying this, they say that okay, this system of equations has a specific solution. And when they say the stiffness matrix is symmetry positive definite, by this they are saying it will definitely be invertible.
Yeah. So the reason could be something mathematical, like
Yes,
for solving a bilinear equation, we can
like
solve.
yeah. So someone may ask like if like okay, you have some set of equations, you are solving this, but how can you, as a mathematician, someone can ask, how can you say that this system has a solution, or how can you say that stiffness
Yeah. So
matrix
if the
is invertible?
okay, yeah. So we
Yeah,
need bilinearity and symmetry.
yeah,
Both things we needed.
yes.
Okay.
These things, at least uh, in the normal solid mechanics and uh, heat transfer, most of the cases we see these things, but these things can break down in some cases when you go for nonlinear differential equations. But in those cases, in order to say that you have a unique solution, you have to come up with different set of conditions. Then only you can say that the solution is unique, or you'll find something like that.
Yeah. Okay. But the condition is it is just like by chance that condition for both bilinearity and to be
Not by
symmetric is
chance.
comes out to
Generally,
this
the
like bokeh metric.
it's like the type of equations which we are solving generally, at least in this basic FEM course, we only solve the stress equilibrium, like elasticity, and then heat transfer generally. Like with these problems, generally we get bilinear and symmetric equations, like symmetric positive definite. And
Yeah.
even
But the
in this,
condition is shown that like that is shown that it is A11 or A12, like those things should be same, and that is the same for getting a bilinear equation, and that is the thing we need to have a symmetric equation.
A11 and sorry, I don't. Can you say the expression?
uh, just a minute.
It's
Yeah, so A12 and A21 in this one variable two dimensional equation, if they are same, then we have a symmetric matrix, and that is the condition needed for bilinear also.
no A12 and A21. It's symmetric. It's fine.
Oh, no, not this.
Okay.
Oh, not this.
Oh, some expression
I
is
need to
there.
show that. Yeah, some
Okay,
expression.
maybe
Expression
if you
is.
can,
Let me tell you the
I will
expression.
tell you. Like generally, bilinear function. If you want to check, the conditions are like bilinear by default means it is a function of two variables. Okay. In order to say if it's
Yeah.
bilinearity, it should satisfy these conditions. Similarly for y. It's basically like if you keep one variable constant and it should be linear in the other variable. Any function, if it satisfies these four conditions, it can be called bilinear function. Okay.
Okay, just I'm writing it now.
Sorry. Maybe if you can say that
I'm
expression.
writing it. Just
Yeah.
actually, I'm just telling you that particular lecture there, which is
Yeah, I think I remember we solved for some general differential equation, right? But I don't remember that expression.
yeah, that is what I'm searching. Just a minute.
Yeah.
It is in week 5.
Sorry, it is in week 5.
In week 5. Yeah, just a minute. It is in 25. Maybe lecture 27.
Problems.
It is not opening.
Yeah, same for
Till then,
Conditions hold
uh,
this one.
dot
Yeah,
comma dot.
this one, right?
yeah, yeah. Like in the last of these things.
So by linear in UW, if A1, A do not depend on U, yeah, these are the conditions. It is bilinear in UW if the coefficient is not a function of U, and symmetric if A21 is
Yeah,
equal to
in
A1.
the last,
Yeah,
yeah, and in the last of this video, please come to the last of this, like a little forward, one slide.
yeah,
When it is completely, yeah, here at this point, yeah, in the last it is written that if Kij is equals to Kgi, if A12 is equals to A21, and
yeah,
here he told that you, yeah, so for symmetric matrix this is the condition A12 equals to A21,
yeah.
and here he also told that this is the condition for the equation, like this, b function to be functional to be bilinear,
No, no,
like
this is condition for
is there,
symmetricity. For bilinearity, the coefficient A11, 12, 21, 22, they shouldn't be a functions of U or W. That's it.
And they also need to be equal, like,
No, it doesn't need to be equal. For
okay.
bilinearity,
And there is
there's
no
no
such relation
requirement.
between.
Yeah, there's no such relation between bilinearity and symmetric. They are just two different properties.
Okay, okay, okay.
Yeah.
Just bilinearity lead to consistent solution and symmetric lead to invertible. Okay.
Symmetric positive, definitely. Yeah.
Yeah, yeah. And the next thing is about boundary condition, like how weight function help to know primary variable.
Weight function helps in primary variable. Yeah. I- Is there any? Hmm, okay.
Like when we form the when the
Yeah.
weak form equation, we have this final
Maybe
weak
you
form
can say
equation.
the
In
final
that
weight
we
form.
see,
Yeah. In the final weight form, we have integral f psi I dx dy. Okay. And now q psi a q n ds.
yeah, in this equation only, if we go backward in the same, like in that lecture,
Okay.
please, in the big, yeah, in the beginning,
Okay. Yeah.
yeah,
You
in
don't have to
our
worry
previous lecture.
about it. Actually, you have this expression, right? Uh,
No, then it will be
you
become
have
very
this.
easy to like to please open the previous
Yeah.
lecture.
Okay.
Yeah, yeah. Just one second.
of
Yeah, further,
divergence theorem.
further.
Integral over the,
After this weak form is
so I will get
complete.
is known by evaluating all, and d2 0 u w ux plus a to
Yeah, yeah, yeah.
understand
Yes,
what
this point, this point.
Yeah.
Yeah, this boundary term. So
Yes.
here he after just after this lecture, he like just after this
kind of
slide, he
boundary
explained
conditions we need
that
to
this
know.
boundary term is actually helping us to know what are the boundary condition. What are the boundary condition we need.
Yes.
So if
Yes.
we take only W, we need it leads to primary that
Yeah.
essential boundary condition, and the second part tell the that we need the
Partial
second part is
derivative of
about natural
w
boundary
with
condition,
respect to its
and
Yes.
time
in the
f1
first part
plus
the W it actually
w
tell
times
about the primary variable.
partial of f1 with
Yes.
respect
So
to
that is
x.
what how it
Uh,
is happening.
okay. Okay. It's like when you take this elasticity normally, if you do the weight form, you will get something like this thing as the force term. Okay. Elasticity. Yeah, in the weight form. So from this, when tells about the primary variable, and whatever remaining it tells about the secondary variable.
Yeah, yes, that is
Okay.
right.
Yeah. So this is fine in like elasticity. We already know beforehand what it is. But let's say you're solving some new problem where you don't know what boundary conditions to use. You can just by like you have some differential equation, random differential equation. Then if you make it to weak form and then you see, just by looking at this, you can say what would be the secondary variable of it. Let's say something like you have this. This is some random differential equation. You know U is primary variable.
Yeah.
What is secondary variable here? We don't know, right? So
Yeah.
when you do the weight form, and if you convert it, like you'll get this term. So whatever comes in this would be your secondary variable. That would be your Neumann boundary condition.
Okay. And about well, like from weight, how weight is helping in knowing the primary variable.
Uh, weight, actually we consider weight is zero wherever primary variable is known.
Yeah, it is a variational.
Yeah. So it's like wherever primary boundary conditions are mentioned, their weight we will substitute it. That's it. Like it doesn't tell you what primary variable is actually. We need to know what primary variable are from the differential equation itself. But it will tell you about the information of secondary variable. But for substituting, you can
Yeah, but
substitute
it is
W is equal
told.
to Z.
Yeah, it is told, but multiple times that W like help
So
you
this
know
gives me
because the same statement is
W
given that
times
where
partial of
primary
F1 with
variable is
respect to
known, that
X.
W is zero.
Yeah, wherever primary variable is known, there W is zero. That's fine. But yeah, wherever primary variable is there, W is zero. It's fine. Then, but
So how
W,
how how it is
how?
like where it is going to come in calculation, and like how it helps, like where we are not making weight zero, we are assuming it to be equal to shape function.
Yeah, we assume it. We are assuming W as Ni, right?
Yeah.
This one, it's actually don't worry about this. Whatever you are getting, something like this you will get. Force term, n transport sigma dot n dx, something like this. You'll get. You can just substitute into this term, and you will get it. What happens is weight is zero. Actually, in this case, the W is NIWA. We change the modify this thing such that W is equals to zero, where NIU is specified. You don't have to worry about these things. Once you come up with this expression, you can just substitute in this. That's it, and you'll be fine.
Yeah, math. Yeah, yeah, that is okay, but mathematically there is absolutely no issue.
Okay.
Hello?
Okay. Yeah.
Yeah, mathematically there is no issue, but
Okay.
the only thing is like physically not making any sense. Like U is no, W is zero. We are not using those things.
Uh, okay. You are saying, let's say, in a bar problem or somewhere, you mentioned here. Is it also some you are? You are saying we are not using this anywhere, right?
Yeah,
Mhm. Okay. Okay. Actually, we will use it some. We have this KU is equal to F format, right? So this term goes to F, right hand side. Okay.
actually, I'm not able to see. Like your
Sorry.
screen is fixed to camera. You have written something?
Yeah,
No, it is
it's
not
not
showing.
visible.
Your camera is also off. Yeah. No, yeah.
No, it's working actually. Maybe. some issue on your side. It is, I have another screen and it's showing in.
Okay,
Uh,
yeah. Please write something.
yeah, is it visible?
No, my screen is fixed.
Maybe you log out and log in better. Probably some issue from your side.
Yeah, okay. Hello?
Is it? Yeah. I,
Yeah, sorry, actually there is an issue.
yeah. Is it visible now?
Yeah, yeah, yeah.
Yeah. So I was saying that when you write it in matrix format K is equal to F, this term goes into right hand side, and whatever boundary condition you have on displacement goes into this one. You have to substitute it, then only it will work. Otherwise, it won't work out.
Okay.
Yeah, it's actually if you don't substitute this, K won't be K like K won't be invertible if boundary condition is not substituted. K is not used. K is not invertible actually. When you substitute this and remove those corresponding rows and columns, then K would become invertible. It's like when you don't use this, by default, K is positive symmetric positive semi-definite.
Yeah, that is okay, but the thing
Yeah, yeah.
is like, yeah, these things are okay. Actually, only doubt is
Yeah, you
like how.
use you in this only. On this
Yeah,
U matrix, you will substitute. You won't like in W, you will like
like
you will write
there
this
is
expression
no,
on.
yeah, there is no such, we are not using that relation that w equals to 0 where you specified, and how u helps to know in the primary variable. Like it is told multiple times even in course 1 also that you help to know what is the primary variable, but that I don't find anywhere. Like we can directly do the mathematics, we can easily find out the primary variable, secondary variable, that is okay. But it
Yeah,
is, this statement is made again and again that,
yeah. I'm not sure about primary variable. Secondary variable, I'm pretty sure. Primary, you have to know it. What like on which the derivative is. That will be your primary variable.
yeah,
And
and one thing is like,
second,
this
yeah,
is very, this is variational, this w is variational. That is a big doubt that how we, if I just replace this w by some variational, and if
yeah.
I start solving this equation, then it, how it is going
That,
to work.
instead of W, if you place something like delta variation
Yeah,
of U, so something like that.
yeah, leave that, like I will comment on it. Like there are some other roots that I will ask you again.
Yeah, yeah.
But
Uh,
about that,
I don't think, I don't worry about primary. I don't think it's, even I don't understand how W will tell you about primary variable. Actually, primary variable will tell you how the W should be. Like it should be zero. Like you should take W such that depending on the primary variable. But based on this weak form, you can tell what is the secondary variable is.
yeah, but it is actually, this statement is made again and again. So I will check that thing and come back to it about this thing. Primary and secondary is okay. Secondary I can.
Yeah, secondary, generally the use of this form, you can know what is the secondary variable is. But
Yeah,
primary, you should know beforehand.
yeah, that is the issue. Yeah, okay. So one thing is like, the next I told that it is said that per internal rotation function needs to be complete polynomial. That is
Okay,
fine, but
okay,
otherwise the result will be inaccurate because they will be skewed in one particular direction. How?
okay, okay. Something like this is especially in like 2D cases, right? Like you have some n of x comma y, and let's say you are taking just x, you are taking x square, but y you are taking only y.
Yeah,
Okay, you are not taking y square. Okay, there will be coefficients everywhere. Okay, some
okay,
function approximation. Okay, it means that in ln x and ln y. So ln x you are doing quadratic approximation, right? And ln y you are doing linear approximation. So obviously ln y it will be less accurate than x. So your solution will be skewed. That's what it means.
yeah, I understand.
Get it right?
Yeah, okay. The next is like about incomplete. Yeah, yeah. That thing is like, if we are in, there is one thing like incomplete quadratic polynomial. In that, a square or a quadrilateral with mid node can be represented by incomplete quadratic polynomial. But it is said that then there are compatibility issues. That's why we are not opting for it. Like, what is this compatibility
Uh,
issue?
Incomplete quadratic polynomials, a square and quadrilateral with mid node is represented by it. But it is said that if we take it, then there are some. Is it something like if you take shape function like one gets a square and just y? For this kind of case, incomplete polynomial.
Yeah, let me check. Yeah, it is C1 plus C2x plus C3y
One
plus
second, sorry.
UX comma अच्छा C1 plus C2x plus C3y plus C4xy plus C5
Plus c5.
x square bracket in brackets x square plus y square.
No.
Yeah, so here two things are told. One is that that such kind of equation is incomplete quadratic polynomials, and
Okay.
they can, but still they can represent two kind of geometries. One is square and the other is quadrilateral with a mid node.
Okay.
Quadrilateral with mid node or
Square or quadrilateral with the nodes at midpoints as well.
no at the center.
Oh, at the center of the quadrilateral.
Yeah,
Okay. Okay.
but in this there are two issues. One is there are compatibility issue. What is this compatibility issue?
Compatibility issue means you let's say you have two elements like adjacent elements. Okay. And at this common edge, the displacement should be same. Right.
Yeah.
Common edge. Like primary variable should be same. So like let's say you solve element wise, you are solving for first element, you come up with a solution on this, and then you solve with a second element, you should get the same expression. If they are not same, then it's like not compatible.
Okay. But for
Yeah.
like square with a mid node, quadrilateral with a mid node, that is will be a problem. But if we have a square, then it is why it is a problem. Square is okay.
Okay. Did he say that with square it's not a problem, but with a quadrilateral it's a problem? Is it?
No. He said both these square and quadrilateral with a mid node.
Both of
Acha,
them.
okay. Okay. He might have said I might have heard it wrong because square it is fine, but quadrilateral with mid node there may
Yeah.
be little.
Yeah.
Yeah.
Probably he
And
said that.
yeah. And the second point here he told is this that we are violating our own condition to be linearly independent because weight of x square plus y square that is c5 is need to be different.
Yeah.
What is the relation to be like it can be anything, and how is this weight is equal? Like if we have a complete like original quadratic polynomial which we use when we use quadratic triangular function, there the equation is like this, the same equation, but only with the coefficient of x square is c5 and the coefficient of y square is c6, some c6.
Yes.
The weight is
Yes.
different.
Yes. Weight should be
So
different. It's like you have x square and y square, and we should be able to change them independent to each other. It's like if you change coefficient of x square, then automatically y square coefficient is also changing, right? Let's say you have some problem where along x and along y they are acting different. Okay,
I
along x
understand.
and y, you get it right. You
Yeah,
have function is different. Then, but in this case, they are not independent. Okay.
yeah. They like,
Those,
but can we like if I write this equation as c5 x square plus c6 x square, please write it
yeah,
like instead of.
yeah, C1 plus C2x plus C3x square plus C4xy plus C5x square plus C6y square. Yes.
Now here if c5 and c6 are same, it could happen.
Uh, yeah, it can happen. It can happen, but by default, we shouldn't take C5 and C6 are same. If it happens
But
naturally, it can happen depending on the problem.
yeah, I understand. But they should not depend on each other. That if one
Yeah,
changes,
we
then
shouldn't fix them that they should be same. If it
yeah.
naturally happens depending on the problem, it can happen.
Okay, I understand. Yeah, that is okay. It will be same, but not dependent. Okay. Yeah. The next is, yeah, about aspect ratio. Like why? Like if aspect ratio is very
Yeah,
big,
yeah,
then it is bad because we have errors and we multiplied those errors by that
yes.
aspect ratio and it will be large. That is okay. But if we have a small aspect ratio, that is fine. It will make
No,
further small that error.
no. When you say aspect ratio, it means that the ratio between the edges. Let's say for we are uh, talking about rectangle. Okay, aspect ratio would be something like A is to B. Okay, ideally it should be like one, like all sides are same. Ideal element shape is square. Okay, it's fine. Uh, every time, obviously, it can't be one because we will deal with complex shapes. So at least it should be close to one. So ideal aspect ratio should be close to one. It shouldn't be too low and too high. At least close to one. It should be. Even if let's say it is too high, it will be like this. And if it is too low, it would be something like this. Both are not good.
No, yeah, that is like in that equation term, it was told that just a minute. Yeah, because what happened if this C by A is become very small, then
Yeah.
A matrix become almost singular.
Yes.
Because it is almost singular, we have the determinant value. Then we find out uh, when we solve the equation, we need to we have a determinant value of it.
Yeah,
So
it's
it
like
is.
if it becomes too thin, okay, the area would be like close to zero, something like that.
No, it
Is it?
like no mathematically when this aspect ratio is very low, mathematically
Yeah.
it will not be a singular because they do not lie on the straight line and it is but it is almost singular. It means
Yeah,
that
it's all.
yeah, it means that the determinant will be extremely small value,
Yeah, yeah.
and when
It's
we are
like
doing the computation, we have round off error and truncation error, and
yes,
then small changes in determinant will cause large error.
yes.
Like I don't understand that how small changes in determinant
Uh,
like
it's when
second doubt
determinant is
like
yeah,
please see the fourth doubt in my what I have. right? That is
Yeah.
of almost similar. It is said the determinant is very small, and since we have this round of truncation error,
Yeah.
in the small change in determinant value will cause large error.
Yes. Yes. It's like when determinant is almost equals to zero, it's not zero, but nearly equals to zero. Then, like whatever, let's say if it is, let's say it is very small, it means let's say it's minus uh, minus 12 or minus 20, and your let's say determinant, and your computer accuracy is in also order of 1e minus 20,
Yeah.
then it won't be proper, right? Like like small changes also affect say like determinant a lot. Like just the like even rounding off error would affect the solution a lot.
Yeah, but if that is the case, we have large. That is okay for large aspect ratio. Like for large aspect ratio, we have determinant value very large,
No,
and it,
aspect ratio I said, right? Aspect ratio just means ratio between length and width. If it is large means like this, and if it is small means it is also bad. Even this is like that would be almost zero, right?
but the why one reason what I told that aspect ratio is bad, small aspect ratio is bad because it makes that A matrix almost singular because the
Yes,
determinant value become almost near to zero.
yes,
Okay, so if I need to explain why this aspect ratio is bad, I would say because this matrix A is going to be almost singular, which makes the
yes,
determinant value very
yes,
small or something like this,
yes,
right? But the
yes,
problem is if it is very small, if it is very high,
yeah,
then I multiply it with y some error, whether it is truncation error or round of error, it becomes countable. But if it is very small, this value is very small, and if I multiply with the round of error or
yeah,
truncation error, it will
yeah.
further reduce the error. So why aspect small aspect ratio is bad? Only large aspect ratio should be bad.
No, no, yeah. First of all, like, are you like, did you understand the concept of aspect ratio?
Only this that they are very close, like almost like in a straight line.
Yeah,
Element become very small,
yeah. So, what do you mean by aspect ratio very small? Is it like less than one or one?
less than one.
Yeah, that's where the issue is come. It is a ratio between the two lengths. So it's like length versus width, let's say. Okay, A, let's say, is 1 and B is 100, let's say. So it is very large like this. And let's say you want, this is your aspect ratio, 0.01. And A, if it is 100, sorry, I'm saying reverse. A is 100 and B is 1. Your aspect ratio is 100, right?
Yeah.
This is like very lengthy element and it's not good. And let's say A is 1, B is 100. Okay. Even in this, it's just the element shape and structure is same. Even in this, det will be very much equals to zero, right? But it's something like this. But generally, aspect ratio of equally one is ideal, and
Why?
probably I guess aspect ratio also when they say they probably take a larger side by smaller side. Okay, so it will never be less than one. Okay, so
Smaller but larger or larger but smaller?
I think, yeah, it is larger by smaller generally. Yeah. So ideal aspect ratio is should be close to one. So if it is close to one, it's like the best element.
Yeah, I further read about it, then I will come back to it because
Yeah, you can say in your terms, if this is the condition they are using, larger side by smaller side. So the smallest it can be is one, right?
yeah, what I'm saying, like if ratio is like how let's say 20,000, or if it is a 0.001, in both the cases determinant will be approximately zero.
Yes.
Okay.
Yeah,
So
it's just that the way you are stretching is different. Like it's either in stretching in x direction or y direction, but area is area, right? And stretching is not good. Both are bad.
okay.
Both are not.
And why? Because determinant becomes very small.
Yes.
And but okay, up to this point it is okay. Up to determinant is zero. With this one doubt is clear that even if aspect ratio is high or low, at the
Yeah.
end we are going to get a determinant, very small determinant.
Yes. Yes.
But how small determinants change in that small determinant cause large error?
Okay. Let's say you have determinant. Let's say 1e minus 20. Okay. And you are somewhere you for finding the inverse you will do 1 by that. Okay, then it
Okay,
will
now
be
it
one.
become big.
Yes, this is fine, but and let's say your machine accuracy is in the order 1e minus 21 or 22. Okay, let's say 21. So it could be 1.1, 1.3, 1.4 randomly, just because approximation around because of round of error. Based on this, 1 by that could be 1e20, 2e20, anything. You get?
Yeah.
Okay. So this one shouldn't be closer to the machine accuracy. It causes trouble because we find inverse, and in the inverse generally 1 by that comes into picture, and
Okay,
like
understand.
you did it right. And yeah,
So there are two issues actually. One, it should not be near to machine accuracy, and the second is it become large. Large after taking in one by determinant, it become large, and
yes,
when we
yes.
truncate or we round off the errors, it
Yeah, even
get.
small round of errors will create larger differences.
Yeah, that is also clear. Yes.
It becomes very sensitive.
Yeah, now this one last out, like while calculating the inverse of matrix, like evaluating constant, an additional 1 by 2 factors come. Like for that, I think you please open the
Where is
lecture,
it?
like in lecture. Let me tell you the lecture number.
Sixth week.
Evaluation of just after aspect ratio thing. Okay, previous week 5. Yeah, in week 5 at 11 somewhere.
Which I lecture?
Okay, week 5 lecture number, last lecture 30 lecture,
Okay.
near to 11th minute. Yeah, here.
U is equal to A
Okay.
times C.
Now,
So
when we
the first
inverse,
thing
he
we
said
will do
just
is
in the
we
previous
will
slide,
develop an
as
expression
it
for A.
just a previous slide.
U is equal
Yeah,
to
here
A times
is C1,
Okay.
C2, C3. We are interested to find the C1, C2, C3. So we take
Okay.
that 1x1, 1x1, y1, 1x2, y2,
Okay.
this matrix to the U side.
Okay.
Okay.
We will inverse it.
Yeah. So in the next slide,
C.
please open.
So the first thing we will do is we will develop an expression for.
Yeah. Here he said that
So
inside
A
matrix there
inverse
are alpha 1, alpha 2, alpha 3. These are
is
okay.
the inverse of that
And
A
here we
matrix,
have this AE,
and
which is
it is equal to
determinant
some
AE.
one
Okay.
over 2 AE
Okay.
When we inverse this
times this
matrix.
matrix, which is alpha
Okay.
1, alpha 2,
And there
alpha
is
3,
two.
beta 1, beta 2, beta
Okay.
matrix, which
Yeah.
okay.
Yeah, this two factor, how does that come after, just after some time?
Yeah.
Just move forward a little bit more. More. Yeah, here when he writes C1, C2, C3, he write 1 upon 2 AE. And how A, this AE, he said alpha 1, alpha 2 by 2. That could be mathematical expression, but how this two, all these things are mathematical, or
Actually, sorry, I didn't say this lecture. Let's see.
Gamma
A is
1
the
U1
area, right?
plus
Of
gamma
the,
yeah, A
and
is the
what
area. And what he does, like instead of alpha 1, alpha
U
2,
is
alpha
equal to
3,
A
when he
times
actually
C.
do some
So
example, he inverse transpose he do. So transpose is same as the thing.
1 second, let me just cut it out. So you took a triangle element, okay, first order triangle element, and then he took linear shape function C1, C2, C3, okay, and U he said UIXI, okay, okay, yeah, it looks fine. Then we are saying inverse of this, it's directly he took it as and what are alpha 1 and alpha 2 and alpha 3?
U is equal
That
to
can be
A times.
calculated is
So
with
A
the
inverse
formula just
1
after
over
that.
2
Yeah, alpha I
equals
is this
Yj
thing.
minus
Okay, okay. This is some
Yj,
actually
and gamma I equals
uh,
minus
Math.
Xj minus
yeah. I think
Xk.
I would say don't worry
Here
about this thing. You just do it in a standard way how you do inverse.
Actually, this formula is used like I have through other
Xj
sources
minus
also.
3,
Sources
no
I have
sorry
seen
2.
after getting this doubt. They
Yeah.
are using the same formula to calculate this thing, inverse and other things.
Alpha, okay, alpha 1, alpha 2, alpha 3. And maybe if you do the inverse, you will end up with these expressions.
And while he calculated, there after just after that he take an example also. Like I guess in the next lecture,
Okay,
maybe
in the next
in the
video.
last, just a minute, just go in the last of the same lecture if
Okay,
we have taken in the same. No, here not in the next lecture.
okay,
There instead of alpha 1, alpha 2, alpha 3, in the row he take this alpha 1, alpha 2, alpha 3 in the column. Yeah, here. Just after some time. Just a little bit more. Yeah, here. Yeah,
okay,
here instead of in row, he has used while in the previous video he has taken alpha 1, alpha 2, alpha 3 in the row. Here it is he is taking a column,
equals 3,
and he
4.
is using 1 upon 2
Alpha
AE and using the same
calculation,
formula. So column,
we know
like row and that column is same.
alpha 2
I'll
equals
like that.
Maybe we can just find the inverse and see how it would look like. I think we just, instead of finding the inverse, we directly wrote how the expression would look like. It's nothing like 1 x1 y1, 1 h2 y2. You can just do this in standard way. Here determinant would be 1 times h2 y3 minus h3 y2 minus h1 y3 minus y2 plus y1 h3 minus h2. It would be h2 y3 minus h3 y2 minus h1 y3 minus h1 y2. And something like this, it would be, we should write this on h2 y3 minus h3 y2 for the first term. Second one, it would be y3 minus y2 minus of.
How you directly write this thing?
Yeah, inverse of a matrix. It's for this one we remove this row and then write the determinant of the remaining one. For this, we remove this column and row and then write the determinant of the remaining terms.
Okay.
It's like cofactor matrix.
Yeah, that was a big method, like cofactor and doing all those things.
Yeah, it's just that thing only. If you do it that way, I think he just he did it in that manner only and just write in the expression as alpha beta. That's it. I think if you do this alpha 1 is h2 y3 minus h3 y2, is it? Yeah, h2 y3 minus h3 y2.
And this 2AE comes out the 2A in front.
To even I think this determinant is writing in terms of this. He tried to write in terms of alpha 1, alpha 2, all those things. By some, in that process, he's getting the coefficient 2. That's it. Don't worry about this. You can do in the traditional manner, however you are getting. It's coming up out to be this manner.
And yeah, okay, that's fine. But how
Yeah,
that determinant is same as area?
this one.
Yeah, determinant is same as area because
Uh, what was the 1 second?
yk some talking about narrow 1 plus L plus u is equal to
because at one
I
point
think,
you said that AE is area.
yeah,
Fine. So it is mathematical deduction. Huh?
yeah, actually, it's like when you have this area is actually this one. And determinant of this matrix.
But that will not be true for if I have a quadrilateral or or something.
Uh, for a triangle, this is the one. I don't remember about what happens with the quadrilateral. I'm not sure, sorry.
Okay, yeah, but it is just mathematical prediction. That is
Yeah,
numerical.
yeah. I would say this one, it's fine. You can just, you understood it. You can just make an inverse normally in a traditional way, how you would do, and then just proceed further.
Yeah, but yeah,
You don't
like
have to
don't.
remember all these things actually.
Yeah, but can you please tell me that thing what you are telling me by determinant? Because I go by very traditional way of doing that factor matrix and all those things.
This
Like if
one,
I just calculate, yeah, if I have that equation of determinant, that
okay,
x2 y3. After that, how can I write this matrix?
this one.
Yeah,
This one, it's like for the first term, if you are
yeah,
writing in the first one, you
yeah.
remove that column and that row, and remaining columns you have to find the determinant. So determinant of this submatrix is x2y3 minus x3y2.
That is okay. Oh,
Yeah,
you have written it so quickly. I think there is some short trick for that thing.
no, no, that's just that is the thing. That's
Okay, okay. I think there is short because it is very lengthy procedure, so that's why I asked if there is some short trick.
it's just that if you write so many times, you become quick in writing this. That's it.
Oh, okay, okay, okay.
It's just that like in this one, if you remove this two, this four would be there, and you need to remember that minus will be present in these four
Yeah,
places.
yeah,
That's it.
yeah.
Yeah, nothing
So
short. Yeah.
that's fine. And one last thing is like when we for force term, if like there is a triangular element and he calculated the force term, and it
Okay.
happens to be that at every node there is an equal share of force. Like if there is small f is the force per unit area on a triangle, then
Okay.
f into area of that particular triangle divided by 3 is the load coming at every node. If it is
Okay.
a rectangle, then f multiplied by area of that rectangle divided by 4 is coming in rectangle every node of that rectangle. Basically, what he is trying to say that
Something like this is your triangle element, and there is some uniform force on this. Something like this.
yeah, let's say call it small f.
Okay. It's
So
like distributed force.
yeah, so f at every node, if there are three nodes at the corners,
Yeah.
at every node the force is fa by 3.
So he's saying F1 is equal to F2 is equal to F3 is equal to F
Fa by
by
3.
F times area by 3.
Yeah, and if it is 4 noded, then fa by 4, equally sharing.
Did he say anything like this should be equilateral triangle and that should be square?
No, 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 no.
Any quadrilateral?
Any quadrilateral, he just driving expression for linear triangular element. And while calculating the stiffness matrix, he calculated stiffness matrix. Then he calculated force term. When he calculated the force term, he said the resultant come out to be this. And
One before. So what happens is we have this whole domain. Force is distributed in the whole domain, but in the stiffness matrix Ku is equal to F, we have only this nodal terms like nodal displacement and nodal forces. Okay,
yeah,
so we can apply force only on the nodes. So what we do is this make it equivalent to a case where force is acting only on the nodes.
okay, and they are equal.
Uh, I'm not sure about if they will be equal every time.
Even he said that there is a physical interpretation to this thing. that in mechanics, if it is a force, if like in a thermal it is
Yeah,
acting on something else,
yeah, it's like whatever the secondary degree of freedom will be, that secondary variable. Like it
yeah.
could
So
be
he
force, it could
said
be
that
flux.
yeah. So he said that force acting on the element at each node is one third of the total force, and each node shares equal amount of load. This is the statement, right?
Uh, I need to check that actually. I'm not sure. I'm not sure if it is only for equilateral triangle and only square. This equilateral triangle and square, it's sure it will be equal. But
I Let me tell
if
you
it is,
also the yeah. You can
yeah,
check. You will check this.
yeah, I'll
I'll
check
just
it.
tell you the. I'm just telling you the number for that lecture number so that it is easy. Like lecture number 33, I guess. Just a minute.
Oh, okay.
Yeah, in 33.
One more thing is that this one should be equivalent. So sum of these forces uh, should be equal to the overall force, which is force distributed force time area. This is the concept. And even here there will be like sum of these nodal forces should be equal to the total force.
So not 32, 32.
Okay. Yes.
For the fourth term. So this now I times 1 minus numerical integration I
Just a minute. Just writing that out.
Is it in 32 or 33?
I guess 33 only.
integral is
Yeah, 33.
integral
Force
of dx
it near
psi j
19 minutes.
plus okay. Okay. So this
Yeah, when he
is
calculated
equal
this
to
force
f by
term,
2a
at the end he writes that it is going to come out to be
integral of alpha I dx dy is alpha I
just yeah here FH
case of
that's right.
diffusion and other
Here
things
he
it will
told
be
the
somewhat
physical
different.
interpretation of this
But if
thing
we are talking
that
about mechanics,
at every
then if it
node
is
we are
force,
going
then force per
to get
unit
FA
area.
by 3 and the same
So then
calculation
the total
after for rectangular
force will be
element
what?
at the end we get FA by 4.
Which will be exerted upon the triangle will be F times A, right? And there are three nodes 1, 2, and 3. So for the ith node, the total force which will be exerted on the ith node will be one third of that total force. Of but what we will discussion. So now
Yeah, basically I said that the concept is this one only. F1 plus F2 plus F3 is F times A. Like total forces acting on nodes should be equal to force times the overall area.
mathematics. So now we know how to calculate the force term and also
Does
the
it mean that for a small element, because it is going to be a small element in the whole
terms
domain,
for
Yeah.
what
so
we idea.
is it kind of thing that for that small area we have some force distributed over that area, and we are assuming it to be at all node instead of distributing at all area. We are
Yes.
trying to assume it at all node.
Yes, it's like we are making it equivalent case.
And then after we also assume it then it mathematically it comes, it is not assumption, it mathematically it comes out to be equally distributed.
Yeah, probably. Yeah, mathematically. Yeah, I will check once again how it comes equal. Like this expression is you understood, I guess, right? Probably F1 plus F2 plus F3 is F times C.
Yeah, and also this
I
thing
will,
like also this thing also one thing is this, that instead of this equivalent you told, that instead
yeah.
of this one, if we assume it to be equivalent to distributed at only